Good morning, let's start. So today, our class is on the subject of cryptography. And I will shortly describe history of cryptography. Then we will discuss about modern crypto system. And we told this is RSA crypto system based on number theory. And we told that number theory is its oldest field of mathematics. It was always interesting, but it was useless. But after developing modern crypto system, number theory became one of the useful fields. And this modern crypto system, it's based on the Fermat's little theorem. Pierre Fermat was French lawyer at Parliament of France. He was lawyer, but he liked math. And many contemporary people of Pierre Fermat asked of him, why do we need this Fermat's number theory? And nobody could imagine that after 300 years, our safety will be based on the Fermat's theorem. So let's start first shortly describe history of cryptology. And here is basic terminology. Plain text, this is original message, and ciphertext, it's coded message or encrypted message. And cipher, you know, this is algorithm for transforming plain text to ciphertext. About key, we will talk later. And cipher, it's to encrypt and decrypt, you know about it. So let's start from history. And history, it started before Christ. And earliest cipher, it's known as Caesar cipher after Emperor Julius Caesar. And it was simple, but it worked until mid-centuries. Of course, it was developing permanently, but main idea was the same. And this idea is to replace each letter by another letter. In case of Caesar cipher, we replacing each letter by 3 units. It means if in the plain text, in the original text, we have A, in the ciphertext, we have D. And in the modern, using number theory, Caesar cipher, we can formulate using modular arithmetic. So first of all, modular arithmetic, and it works only on numbers, not only on letters. And that's why what we need first of all for any cipher, it's first of all to give code for letters. For example, this is one of the examples. A, we can give number 1, B, 2, and so on. Z, this is 26. And by modular arithmetic, by modulo, we can describe ciphertext as the following. C, and C, it's cipher letter, and M, this is original letter, and C equals M plus 3 modulo 26. So what it means? For example, if M is 1 and 1 is letter A, 1 plus 3 is 4, and to get cipher letter C, we should add 1 plus 3 and find remainder when we divide it 26, and it's 4. And 4, it means in letter A, we should replace by letter D. Okay. And any idea if we got ciphertext, cipher message, how can we decrypt? How can we decrypt this message? Can you give formula like this formula from modular arithmetic, using modular arithmetic to decrypt message?
Just
First,
change plus with by minus and -3.
oh, very good, very good. Andrew got it absolutely right. I agree. So if we have cipher message C, and we will subtract 3 and then find remainder by dividing 26. So it's, you can see it's very simple cipher, and we will not talk more about it. I just would like to show you how very famous phrase of Caesar, veni vidi vici, it can be transforming in the Caesar cipher as the following symbols. Next, it was Augustus' cipher, and Augustus decided it's enough to shift letters by 1 unit, and its cipher, it's based on the same idea to substitute letters. And difference is that in case of Caesar cipher, we shifted alphabet by 3 units, and in this case, only one unit. And famous and favorite phrase of Emperor Augustus, festina lente, it looks as these symbols. Festina lente, it sounds very nice in Georgian, ichkarenella. Queen of Scotland, Mary Stuart, developed her own cipher, but idea was the same. It was more complicated, but idea was the same, and idea was to shift alphabet. And unfortunately, opponents of Mary Stuart broken this cipher, and her head was cut off, unfortunately. Maybe you know this history. And what is main fault and what is the main drawback of these ciphers? Basic drawback is that all these ciphers, they can be broken in easy way by crypto analysis, and particularly to use frequency distribution of letters. frequency distribution of letters, it means that in any language, when we have enough large text, all letters have their frequency to use. For example, in English, highest frequency of use have letter E, and most least used this is Q and X. And by this distribution, using this distribution, it's very easy to decrypt, to break all ciphers based on the idea that all letters are shifted by the same unit. Next generation of cipher, it's called polyalphabetic cipher, and it was developed in mid-centuries, and it's based on the idea, it was significant improvement, and it was on the idea that here we are shifting letters, but in cipher of first generation, we shifted letter by the same unit. And here in new generation cipher, we have keyword. For example, we want, for example, to cipher good morning. And we have keyword. This keyword, let's be bed. And we are writing this word below plain text, and plain text here is good morning. And we are writing it continuously. And we converted it in the numbers. B, it's 2, E5, D4. And we're writing down it below. And then, for example, G. Below G, we have 2. And letter G, we are shifting by 2 units. And we got letter I. The same when we need to encrypt letter O. Below O, we have 5. And we should shift O by 5 units. And advantage of this cipher is that frequency distribution is flat. And it was very significant improvement in history of cryptography. And this idea, it was used until 20th century. And a very famous German crypto machine, Enigma, maybe you hear about this machine, Enigma. It was based on this idea of course, it was more complicated than this our cipher, but idea was the same as in this polyalphabetic cipher. And this German machine, Enigma, if it was used even during World War II. And it was broken, this Enigma. And this history of breaking Enigma machine It's quite interesting, and it has two heroes, this machine. It has two heroes, forgotten hero, and tragic hero. Forgotten hero of this history is Polish mathematician Marian Rejewski. He was first who broke this machine enigma, but Nazi German permanently made this algorithm more complicated, and to break it, it was more harder and more harder. And Polish government decided to share this information with their allies. And fortunately, in Great Britain, lived and worked young genius mathematician Alan Turing. And I mean Alan Turing when I told about tragic hero of this enigma history. Alan Turing was gay, and in 1952 he was convicted, and he offered to choose type of sentence, prison or chemical castration. And Alan Turing decided chemical castration, but he was very depressed, and after 2 years, he committed suicide, killed himself. After 55 years, officially, British government apologized for punishing Alan Turing, man whose genius saved lives of more than 10 million people during World War II. So this was history before RSA algorithm.
I have a question. As I know, there exists a version that Alan Turing was killed by poisoning the apple. So, can it be true?
Salome, he committed suicide, Alan Turing.
But as I know, he eated the poisoned apple. So maybe it was poisoned, not.
I don't know, Salome, I don't know, but what I know that he committed suicide, but maybe.
Okay.
Sorry I'm late. My computer crashed.
Okay, David, it's recording and you can listen then.
Okay, I tried to come
Okay,
in the first.
we are talking just about history of cryptography, and now it was new era.
Which ones? I just want to know which ones did you talk about? There's the Caesar cipher, the Vigenère cipher. Those are the only two I know. Were there any other ones you brought up?
Yes, you can listen it, David, and let me to continue now, okay? You can, this video is recording and I will upload on Canvas link, and you can listen this 15 minutes. So now, you know, life in general, any science, technologies, developing permanently, continuously, but sometimes they are revolutionary leap forward, revolutionary improvement. And this revolutionary step forward, leap forward. It was when these three American mathematicians, Rivest, Schemmer, and Adelman, developed new crypto system, and they published it in 1977. And what is idea of this crypto system? Now I prefer to share my whiteboard. For example, if I will ask you, it's based on the idea that it's easy to multiply two prime numbers, but it's more hard to factorize product of two prime numbers. For example, if I will ask you to multiply 31 by 37, it's very easy, especially using calculator. We can multiply it in few seconds. However, if I will ask you to factorize this number by two prime numbers, we should admit that it takes more time. And this number is product of these two prime numbers. So we can see that in case of two digits, when we have two-digit prime numbers, it's very easy to multiply, but to factorize, it takes more time. And you know very well that prime numbers, we have infinite prime numbers. And question is, what happens if we have not two-digit prime numbers, but, for example, 500-digit prime numbers? And in this case, happened that modern computer can multiply 500-digit numbers in few seconds. But to factorize product, it's impossible in real time. It needs century to factorize for modern computer to factorize product of two 500-digit numbers. And this is one of the basic ideas of this algorithm. I already told about Fermat's theorem, and also third main idea on which based this algorithm, it's Euclidean algorithm. What we did in last week, to be more exact, extended Euclidean algorithm. Okay, now let me now to describe this algorithm. And here we will now use fictional people, Alice and Bob. And these fictional characters was used by these three American mathematicians when they first described this algorithm, RSA algorithm. So, for example, Ellis decided to set up cipher. And this Ellis takes two prime numbers. And for our educational purposes, let's take small numbers. And for example, two prime numbers, P equals 11 and Q equals 2. So Ellis takes two prime numbers, P equals 11 and Q equals 2. Then she multiplies these prime numbers and it equals P times Q, and this is 22. Ellis also need one number, and this number is denoted by E, and this number must be relatively prime with number. Let's denote this number by W, and W it equals P minus 1, Q minus 1. So E and W, they must be relatively prime numbers. So I can write here the greatest common divisor of E and W, it must be equal. So in our case, what is W? W is 10. W is 11 minus 1 times 2 minus 1, and this is 10. So number E, it should be relatively prime with number 10. And let's take E, smallest number, which is relatively prime with 10, it's 3. So let's take E equal 3. Okay. Now Ellis has everything to encrypt, but not everything to decrypt. About decryption, we will talk later, but first let's discuss about encryption. Now, these two numbers, 22 and 3, they are public numbers. So let's now emphasize what is public numbers and what knows only one person, Alice. 22 and 3, they are public numbers, but only Alice knows how she got this number 22, and she multiplied 11 by 2, and only Alice knows how she got this number 3. How she got? She find this number W by multiplying P minus 1 times Q minus 1, this is 10, and she found this number E. This number, it's very important. This number is public key. For example, during war, intelligence service can public this number, can place these numbers on the website and ask people, ask population that please, here key, public key. And if you have some secret information, encrypt this information using these numbers and send this encrypted information to make it safer. Okay, now let's Bob decided have some information, Bob. For example, Bob have information during war that there is something wrong. And for example, bed. He want to send message bed. Okay, first of all, Bob converts this number, converts this word, these letters, converts to numbers. So we know B is 2, second letter. So we can denote it by 0, 2. A, it's first letter, and we can convert as 0, 1. And D, it's fourth letter, and we denoted it by 0, 4. So this word has Bob. Also, Bob knows public key, and his goal is to encrypt this message bed and send to Alice. Bob, I would like to emphasize again, Bob does not know two numbers, P and Q, and how Alice got these numbers, 22 and 3. But Bob knows these numbers, and these numbers are enough. These numbers are enough to encrypt message. Okay, so now to decrypt this message, here is very easy step. Number 2, Bob should find this to cipher this message. Here is formula, and this is according RSA algorithm. Ciphertext equals M, let's denote by M, plain text, M in the power E modulo N. So this is general formula. In our case, C equals, in our case, I mean, now I am trying now to encrypt one letter B. And in the same way, we can do 4 letters A and D. But first, we are encrypting letter B. So M, this is B, and B is 2 in numbers. So it's going to be 2 in the power 3 modulo N. N is this public key 22. And you know very well this is 8. This is 8. So Bob encrypted letter B, and this is 8. And 8 and he can send just 8, or can find correspondence letter in the alphabet, letter with number 8, and send this letter. Okay, so let me now to this message encrypt and decrypt only for one letter A, and in the same way can do it for other letters. Okay, so now Alice got this message. Alice got this message, 8. This is encrypted message. And now she wants to decrypt this message. To decrypt this message, Alice has advantage against all population. Alice knows P it's 11, and Q it's 2. And to decrypt this message, Alice wants one more number. This number is denoted by D, and Alice not such number D, such that E is inverse of E modulo I have here question. Two choice test. What I should write here, modulo W or N? What do you think, W or N? What I should write here, W or N? So what I'm looking for? I'm looking for number D. Only one person in the world, Alice, knows P and Q. Everyone can find this public key, 22 and 3. Everyone knows these two keys, 22 and 3. And only Alice knows P and Q. That's why I told that only one person in the world, Alice, can find this number D. Only she can find this number D. Now my question is, what I should write here, W or N? W is P.
W. It must be
W.
Yes, very good, Salome. Yes, very good. Here must be W, because if here would be N, everyone who knows our modular arithmetic, what we passed in last week, everyone who knows our elementary modular arithmetic, elementary number theory, can find number D. But only one person must know how to find it, because only she knows these numbers P and Q, and only she can find W. Okay, now let's look what is in our case. In our case, we know number E, this is public key, 3 times D, congruent 1 modulo W. And what is W?
10.
Yes, W, it's 10. Okay, now we know how to find this inverse, and let me recall that this D, it's called inverse of 3 modulo 10. And also, I missed to emphasize that this D, it must be positive. D must be positive. Do you remember our example? We got by extended Euclidean algorithm, we got negative inverse, but in easy way, then we found positive inverse. Any idea what is D? So, of course, we can do it by Euclidean algorithm, but here we have small numbers, and maybe you have idea what can be D. By the way, D, it's not unique, but for our educational purposes, D, we should try to take small number. Any idea what can be D?
7.
Oh, very good, very good. 7. Why 7? Because D is 7. And why 7? It's 7 because 3 times
21.
3 times 7, it's 21. And 21 congruent 1 modulo 10. And it's easy to understand because we know that 21 minus 1, it's 20, and 10 divides 20. Okay. However, so we know that this is 7. However, let's find it using our extended Euclidean algorithm, because it's not always possible, of course, to find verbally this number. And let's recall how can we find it by our extended Euclidean algorithm. And to find it by extended Euclidean algorithm, I should choose another board. So let's rewrite here what we need. So we have 3 times, I hope you wrote down it, 3 times D congruent 1 modulo 10. And we need to find number D. So according our Euclidean algorithm, we dividing 10 by 3. So 10 equals 3 times 3 plus 1. It's obvious. And now my goal now is to represent it like A times S plus B times T equals 1. So if I will represent it in this view, then I can write down that it's equivalent, this expression equivalent with the following expression: A times S congruent 1 modulo B. So now I'm trying to represent in this view, and I think it's quite easy for you. I can move 3 times 3 to left side, and I can write down that 3 times minus 3 plus 10 times 1, or just 10, I can write just 10, equals 1. Okay, now from this expression, what is D. What is inverse of 3 modulo 10? This is negative 3. This is negative 3. Compare with this expression. When I represented A times S congruent 1 modulo B, this S and this S, they are the same. So here we have that D equals minus 3, but we know that we need D only positive. And to get D positive, we should add 10. We should add 10. And why we should add 10? I can explain it. 3 times minus 3 plus 3 times 10 minus 3 times 10 plus 10 equals 1. So what I did, I added 3 times 10 and then subtracted the same. Now, from these two expressions, we can write down, we can factor out 3, and we can write down that 3 times 7 plus 10 times minus 2 equals 1. And from here, now I can conclude that 3 times 7 congruent 1 modulo 10. Please, if any questions, ask, because you know it's very important, especially when we have problems with big numbers. Okay, so now Alice now has everything to decrypt this message. And what Alice has, let's write here. Alice knows number P, it's 22. Alice knows number Q, it's 2. Alice knows E, it's 3. And Alice has just found number D, it's 7. And of course, Alice knows number N, it's, oh, I made here a mistake. P, it's not 22, but
It's
11.
11.
And Alice knows number N, it's 22. And now Alice has cybertext C, and she must decrypt this message. And to decrypt this message, according RSA algorithm, our formula is that M equals C in the power D, C in the power D mod N. So in our case, M equals, in our case, M equals C, it's 8, 8 in the power 7 mod 22. Please now use your calculator. 8 in the power 7, it's enough small to find it in your calculator. And please tell me, what is this M?
must be 2.
It's 2 or it must be 2?
It's 2.
It's 2, yes.
Both. It must be 2 and it's 2.
Yes, because B was.
Yes, because we encrypted, not we, but Bob encrypted message 2, and then Alice decrypted, and Alice must get number 2. Okay. If here, so now 8 in the power 7, 8 in the power 7, 8 in the power 7, it's 8 in the power 7 mod 22. And it was possible to find on our ordinary calculator. However, let me to show other way using modular arithmetic. When we have here big numbers, such numbers that it's impossible to find in the ordinary calculator. How can we find it using modular arithmetic? And using modular arithmetic, we will use properties of congruence. And first of all, this number 7, I should represent as powers of 2. So 7, it's 2 in the power 2 plus 2 in the power 1 and 2 in the power 0. Okay, now what I need now? I will write down it like this: 8 in the power 4 plus 2 plus 1. So I should find this remainder. Okay, now to find this remainder, I will use formulas of congruence, but first I need to find 8 mod 22. It's obvious. It's 8. Okay. Then I need to find 8 square mod 22. It's also obvious. And what is it?
$20.
Yes, absolutely. It's 20. Because 8 square is 64. And when we dividing 64 by 22, remainder is 20. Okay. Now I will use I need to find now 8 to power mod 22, and now I will use property of modulo, and I will write it this like this. It equals 8 square modulo 22 square mod 22. It equals. We already know, this is, you can see, this is property of congruence, what we discussed in previous class. And here we already know that this is 20. And also we know that 20 square is 400. So we need to find 400 modulo 22. 400 modulo 22. 400 modulo 22. It's 4.
Four.
4. Very good. It's 4. Okay. Now, to write down now our remainder, 807 mod 22, it equals, according our property of congruence, what we discussed, it's 8 in the power 4 times 8 to the power 2 times 8 mod 22. Now I will use our property and it equals 8 in the power 4 mod 22 times 8 square mod 22 times 8 mod 22, and this is everything mod 22. It equals, and we already know this is 4 times, it's 20 times 8 mod 22. Now, please find your ordinary calculator and multiply it, and we should get 2. If everything is correct, we will get here 2.
Yes, it's 2.
Okay.
Why we have 22 here? Shouldn't it be 20? In where you multiply 4 by 20?
Yes, Katie. Thank you, Katie, very much. So here must be 20, of course, because 4 I got from here. It's 4, and it's 20, and it's 8. It's 20. Yes. Okay. Now let me to give one example. So I would like to ask you to as homework. I will give homeworks, but also I would like to ask you to look very carefully. This video is recording, and realize if you have any questions, ask on Friday. Okay. Now, let me to give one problem. And for example, Alice set up that P equals 3, Q equals 5. So P equals 3, Q equals 5, and also Alice needs to set up number E. And to set up number E, it must be relatively prime with number P minus 1 and Q minus 1. P minus 1 times Q minus 1. So what do you think? E equals 3. Does it fit this number? Can we take E equals 3?
Yes.
Why, Andrew? Because P minus 1 times Q minus 1, it's 10. Oh, no, sorry, it's
8.
It's 8. And 8 and E, they are relatively prime numbers.
Mhm.
So now, Alice now gave public key to Bob. So public keys are N equals 15 and E equals 3. And for example, Bob wants to encrypt message M equals 7. Please, now let's try to encrypt this message. Do you remember our formula for encryption? Our formula for encryption is here. And please write down it. No, it's decryption. And this is encryption formula. M, this is plain text. And to get encrypted message, we should raise in the power, M in the power E, and then find remainder by dividing N. Okay. So please, what is our cipher message? C in this our case, it's 7 in the power 3 mod 15.
It's 3.
What is Android? It's 3?
Yeah, it's 3.
Okay. Can anyone confirm it?
Okay, okay, let's see. I'll try. I'll open up a
I
calculator.
think it's 13. I plugged in a calculator in.
Yes,
Hold on,
yeah,
hold on.
it's 13.
7. Okay,
7 in the power 7, David. 7 in the
7
power.
cubed
So 7
divided
times
by
7.
15 is 2. Okay, it's 2.
So let's find 7 to the power 3.
Times
7 times
7.
7 times 7. It's 343. Then 343 we should divide by 15. Let's divide 15 and we have 22. And what is remainder? I will see now. 22 now I should multiply by 15. So 22 I should multiply by 15 and it's 330. So remainder is 13. Do you agree, David? So here we have not 3, but 13.
I agree.
Do everyone agree that we encrypted this message 7 and we got 13? Okay.
Yes.
Okay, if you agree, so you got this message, Alice got this message, 13. Alice got this message, 13. And now Alice wants to decrypt it. To decrypt, Alice wants number D. Number D. So Alice needs to find W, and W in this case, it's Alice knows P, it's 5, and Alice knows Q, it's 3. So W here, in this case, it's P minus 1 times Q minus 1 Q minus 1, and it's going to be 4 times 2. It's 8. Okay. Now, how can Alice find number D? Formula for number D is that E times D congruent 1 modulo W. So in our case, 3 times D congruent 1 modulo 8. Now, what is D? What is D? What is D without Euclidean algorithm? Let's find verbally what is D. So D is number, positive integer, such
It's
that
3.
So let's check Irakli. And in Irakli's opinion, D is 3. 3 times 3, congruent 1 modulo 8. It's true. It's absolutely true. So here is a little confusing that these E and D, they are both the same. It's happening very often when we have small prime numbers. But don't pay attention, no problem. So now we need to find now we need to decrypt message and find original message M. And M, we know basic formula, C in the power D mod N. Please pay attention and don't confuse. Here we have mod N here. Also here we have the same mod N, and only here in one case when we want to find D, we have not N but W. So from here, M equals 13 to the power 3 mod what?
15.
15. 15, thank you. And now you can check it in ordinary calculator. We should get 7. It must be 7. If we did everything correct, it must be 7. Any questions?
So what will be our homework?
Salome, I will upload.
Oh, okay.
I will upload. Right now, I will upload. After 20 minutes, it will be uploaded on Canvas. Okay, if no questions, let's finish today. And if you have any questions, our next class, we will start to answer your questions and prepare your questions. If something is unclear, we can do it again. So prepare your questions for next class. Okay, let's finish today, and thanks for joining, and have a good day.
Goodbye.
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 Bye.
Goodbye. Thanks for the lecture.